No, we probably won't. I mean, it's fine. I just don't like postponing and postponing and postponing and postponing.
Okay, we'll make it a hard Friday.
A hard Friday.
Hard Friday, guaranteed.
Okay, guaranteed Friday. All right.
So this Friday?
I can say with 100%
This
confidence that it will be on Friday between 4 and midnight.
How many samples do you have, though? Are we talking like T confidence? Or are we talking
Let's talk about student confidence.
Yeah.
So, the central limit theorem tells us that for large sample size n, the distribution of the means is Gaussian. That was what the last lecture was all about. However, for small sample size, the Gaussian isn't as good of an estimate. Students' t-distribution is superior for lower sample size and equivalent at higher sample size. Technically, if the population standard deviation sigma x is known, even for low sample size, we should use the Gaussian distribution. However, this rarely arises in practice, so we can usually get away with an always t approach. It's actually really rare that you're going to have the population standard deviation sigma x. So in practice, it doesn't really arise that much. But technically, if you are given sigma x, you should use the Gaussian distribution. Just doesn't arise very much. A way that the t-distribution accounts for low n is by having an entirely different distribution for each n, which seems a bit of a cheat to me. I mean, it's just like, oh, we're just going to have a totally new distribution for everyone. But, you know, whatever. Actually, instead of n, it uses the degrees of freedom nu, okay? Which is n minus the number of parameters required to compute the statistic. Since the standard deviation requires only the mean, for most of our cases, we will use nu equals n minus 1, because we only needed the mean. So that's why these tables don't usually have n in them, they have nu in them. As with the Gaussian distribution, the t-distribution's integral is difficult to calculate. Typically, we will use a t-table, such as the one given here. And this is a hyperlink, but I can't click on it in this program. So I gotta open up.
Doesn't open.
It doesn't open?
No,
What?
not here anyway.
Psh. I don't believe it. I'm going to try anyways. Not that I don't think you're good at clicking on links, but I
I was clicking on it on a piece of paper, so it was just a snarky.
So I take it back. You are bad at clicking on links.
Yeah.
Oh
I can't play Zelda. Oh my god, it took me a second. Dang it.
Man, I didn't even catch it.
I can't believe I didn't catch
Do you not used to you get it now?
I don't really play Zelda. So I don't even know.
it was just about clicking on links.
Oh,
Yeah, that's all.
Oh my goodness.
Gotcha.
Dang it,
We'll move on.
you know, I have to. Like, we should probably have like an appreciation day for your humor. It is really good. I do like it.
Where's mine?
Who? Oh man, oh man, it's getting snarky today. just keep walking. Okay, so I need to move this over. Okay, so now we can see my face, which was important. And this is the tea table. I didn't get to making a tea table because I wanted to get a little bit of sleep last night. So instead, I clicked on this link here, and this is on the interwebs. So I recommend looking at it. It's a nice one, but notice that the table looks a little different. We have degrees of freedom in this column, sometimes it'll just have new, sometimes it'll just put n there, but it should be degrees of freedom. So the first column is degrees of freedom.
Which is one less than your.
Usually, yeah, one less than. So when we're computing our confidence intervals, it is, because we're talking about the standard deviation t value, and for standard deviations we have one parameter, the mean, that goes into that statistic. Therefore, it's n minus 1 degrees of freedom.
Okay.
Yeah.
I thought like for the new it was like n minus like an n plus 1, like where n is like the exponent on like your linear representation of your data. That's what like said in the book. So like if you got like a line, the exponent on your like x value is 1. So you have like a 1 plus 1 minus, or n minus the 1 plus 1 quantity.
I think that what that is, so I don't remember that from the text, but I'm sure it's in there. I'm guessing they're referring to is that, so you can define the degrees of freedom in different ways,
Okay.
but it is equivalent. So if you had a polynomial of order m, then you would have m coefficients in that polynomial, and so that would be m parameters that come into that polynomial's function expression, which for the standard deviation we bring in one parameter, and it's the mean, so that's why we use 1 in that
Okay.
expression. That would be my guess, but I would have to look to double check at what they're referring to specifically. There are a couple different ways of framing degrees of freedom. I've always liked the number of parameters that go into the statistic you're trying to find the t-score for. I think that one's the one that's maybe the most intuitive, or yeah. But there are other ways of defining it, and I should look and see, and I can follow up on Slack with you if you want.
Okay.
Be happy to. Yeah. Cool. So degrees of freedom. So that's the first column here. We look for that. So say we had an n of 20, we would say, oh, our degrees of freedom is 19. So we would be working this row right here, right? So this row. I ran out of trackpad. There we go. And so we've got a table that the values in the table are once again, well, instead of being z-scores, they're t-scores this time. Okay, so you can think of them in the same sort of sense. Number of standard deviations from the mean, that same interpretation as the z-score. However, instead of having the two dimensions of the plot be decimal places, which is what we use in the z-score chart, or the table for z-score, we have one of them taken up by degrees of freedom, right? The vertical one is taken up by degrees of freedom. So we don't have another one because people don't really like three-dimensional tables very much for whatever reason. So we're stuck with just one dimension to represent the z-score values. And another thing that's different is that what we care about when we do t-scores, and honestly often z-scores, but z-tables have a long history of being set up the way they are, so people just leave them that way. But what we usually care about is finding the t-score for a specific confidence or probability interval. Okay, so or value. So we might care about like a 90% probability t-score, or which is equivalent to a 90% confidence t-score, right? Or we might care about a 99% confidence t-score. So what they do is they actually, instead of having it set up the other way where you have the z-score sort of on the columns or on the rows, and then having the probabilities in the table. It's the other way. So the probabilities are the columns, and then the z-score, the t-score, is in the table. So it's kind of like everything is opposite of what it was, which is confusing, but it's virtually the same thing. Is there like a lot of echo in here today?
What?
It sounds echoey to me in here today. It's strange.
It's just the big extra
Maybe I insulted Jordan on accident. I only do it out of love, Jordan. I never mean it in any hard way.
That's
There.
the typical student thing, and ask you to repeat that. Not the thing you said about Jordan. The thing you said about how to read the T table.
Yeah, so let's go back and remember what our T table looked like. So if you guys are like, where do I find the T table again? I will show you. On the measurements page, that there is now an appendix with the Gaussian distribution table in it. There's also going to be a T table here one day when I have time. And notice that the z-scores were on the header of each row, and then so the tens decimal place in each row, and then the hundreds decimal place in each column. So what you did in the table typically is you looked up a z-score, and then you figured out, okay, this is the probability. This is the shaded region there. That's the probability associated with that shaded region. Well, we flip all that around in this T table, and we say, okay, you got to look up, first off, degrees of freedom's in there, which it wasn't in the Z table. And then you got, instead of finding your z-score and then finding in the table the associated probability, you start with your probability, and then you look for the the score associated with that.
With 95% confidence.
Yeah, so
at 19 degrees of freedom, I have the blah value.
right. So 19, if that's your degrees of freedom, and you wanted a 99% confidence, you would be looking at a t-score of 2.861. And actually, this is really set up. Remember how we did two problems for the z-score? We did one problem where we started out with the essentially the interval that we wanted to find the probability in, and we looked it up, and it was really easy to use the table that way. We essentially just like looked up the value in the table, and it was easy. And then the other way we did it was we started out with a probability or confidence level, and we wanted to know the interval. And we had to use the table like backwards, and we had to look up the probability in the middle there, like, oh, where does 95% show up? And then we had to figure out the z-score associated with that. This is set up for the second type of problem. It's set up so that it's easy to be like, okay, because usually what we care about is what's the interval over which we can have a certain confidence. Like maybe I want something that's like, give me an interval where I can be really confident. Give me a 99.9% confidence. Well, that's your t-score. If this is how many this is your sample size, 19. Yeah.
And you might get to this later, but don't the t-scores get used in the same kind of way as uncertainty values, where they get like the sum of the squares?
Yes. So.
The square of the sum of the squares thing.
Yeah, and your lab is slightly ahead of us right now. So you guys are doing some uncertainty analysis right now. So you're using this in there, but you do use the t-score. T-score is the one that is typically used for the confidence interval, but then also in the uncertainty analysis. So yes. And so the t-score value is really useful to be able to find. So I typically, we don't want to be working down here in this 50% confidence. We like having more confidence in our confidence. So we like to be up here. And so we're in these later columns typically. We also like to be working with higher degrees of freedom here, right? That's where we ideally be. And notice that as we go down, so as our degrees of freedom increases, as we go down the table here, these numbers are decreasing, which means our t-scores are decreasing, which means that we have a smaller and smaller bound on our what our confidence is. So it's good. It's good. We go down the chart, we like that. Up the chart, we get nervous. We get nervous down in here. We don't like to be with degrees of freedom like 5. That's not great. Notice that when you go down to 1, it's like, yeah, you don't know anything. Look at that. You want 99.9% confidence, if you have a degree of freedom of 1, your t-score is 636. You're saying you have confidence, 99.9% confidence, of being 636.6 standard deviations from the mean.
More than one, less than a bit.
Yeah. It's like, you don't know anything at this point. Also, this model kind of breaks down at those very, very low values. Your assumptions are usually not very good. So, okay, these are, and these are really commonly used in a lot of statistical analyses. So this is across science and engineering, this stuff is used. So confidence turns into uncertainty analysis. We also will have a, when we look at paper results, research papers that say, I have a probability, so you'll see the p values will come in. That also has to do with this chart. Okay, a note on these charts too. The values that are given in most of them, there are two different types that could be given. Sometimes they give you the tail values here. So this one gives both. So it gives these tail values. So 25% means that this is the probability of being in this tail here. 0.005% is the probability of being in this tail. It's essentially the probability of it not lying in your confidence interval, right? And that's one way to go with it. The other side is your confidence level percent, right? And that's what we usually think. This is usually what we think about. These are two-sided, typically. Meaning, remember how we had to subtract the upper limit, the lower bound from the upper bound distributions to subtract off the tail in the z table? We don't usually have to do that in the t-table because they're thinking you're always going to be symmetric about that center, and so they put the values in there for the symmetric assumption. So this table entry for p and c is a critical value t star with the probability p lying to its right and the probability c lying between negative t star and t star. We've been calling it b for bound, like z sub b for bound. T sub b is what we usually use, but they do star for the bound. So they're saying it lies between t star and negative t star, which is exactly the interval that we're interested in. So the t-table is set up exactly the way that we wish the z-table was set up, because this is the direction we usually want to go. So it's set up to do the types of problems we want to do. Okay? I think that's all that I wanted to say. Yeah. So let's on the fly do a little bit of this. So let's write a MATLAB script to generate a data set with 200 samples and sample sizes being 10, 20, and 100 using any old distribution. So we could use like uniform, for instance. And then compare the distribution of the means for different n. So those 3 values of n that I gave. And then use the sample distributions and a t-table to compute 99% confidence intervals for each of those cases. So this is like kind of like what we did before, but for t-table, right? Should be pretty straightforward. So let's fire us up a little MATLAB. mean, I felt like I was firing it up, but maybe I wasn't.
What do you mean by sample sizes n equals 10, 20, and 100?
What I mean is,
How many we're picking out of the 200?
so remember that a sample is a bin, essentially. So we have this data, and we're essentially taking them in batches. So a sample is a batch of data. And so when you say sample size of 10, it means that you have 10 data points in each bin. 200 bins. So I'm saying 200 bins, so 200 samples, and then 10 data points in each bin, try that case. 20 data points in each bin, try that case, and then 100 data points in each bin, try that case. MATLAB is not seemingly popping up for me, so I'll try one more way here. It's very weird. Never had a not launch before. It's weird. Pretty fun. So,
Just shout it out loud.
okay.
Put your clothes off. Where are your colons, dude?
Okay. I have an alternative possibility here. Ooh. I may have figured out why this is happening. I might have a notebook open that
90 tabs. Yeah. Like 90 tabs on top of 90 tabs. 2 pages of 90 tabs.
I know. Yeah, I know. I mean, you're not wrong.
I think you're going to have enough
The thread counts a bit strained.
Like you need 32 gigs of RAM.
Okay, so what we're gonna do is something fun here. We're gonna do. That was good. Nope. Notebooks. There we go. Now I just need to do this. We'll run MATLAB inside of this,
I hope my
he
English
said.
brain will understand that sciencey shit. That was amazing. It just blew my mind. Hit in 14 seconds. Nothing. Literally nothing.
Okay. Well, we're running MATLAB in a browser because that was apparently the only way I could figure out how to do it right now. So we're doing that. Let's generate some data. So first off, we want to define some parameters. So let's say we're gonna do number of samples. We'll call it n. I said 200 in the problem, right? And then we got to choose our n array. So we have like 20 minutes. We probably have time to do it right and do an array of n's and then do loops every time and so that we can compare stuff directly. Should we do it that way, or should we do it the way where we like change the n at the top and then rerun the script?
I like to change it at the top.
No, it's for loops.
Let's do the for loop. That means that you guys get practice doing something that would be harder,
Yeah.
which I think is good. Okay, so NA equals, we had 10, 20, and 100, right? N underscore A means N, which is an array. I like that. That's just a little idiom I use, but you don't have to. So then,
It means it to you, not to MATLAB.
that means it to me. Exactly. MATLAB does not care.
Yeah, but some stuff means stuff to MATLAB.
You are correct. MATLAB has feelings too. So, okay.
I must have heard school. Yeah, you screw you, man. I know it crashed.
And now we want to generate the data set. Let's generate the data set with a mean, shall we? Because I think so. A mean and a standard deviation. Should we make each of these data sets be normally distributed, or should we have them be uniformly distributed? What do you guys want to use?
Uniform.
Normals?
Normal.
Uniforms?
No one wants to be a normal.
Ah, it's a tie. We're gonna do normal because I want to do normal because we did uniform last time, so I want to mix it up. So, so we need to choose a mean and a standard deviation of it. So, let's do mu x. Well, I'll just do mu. Let's just call it mu. Mu is equal to, let's call it 27. Is that what you said? Okay, 27. And let's make a standard deviation 9. I like it. So this is our data set. We need to generate this random data like this. So let's call it our data array. And what we need is, what we're going to do is we're going to actually generate one large data set with the highest sample size, and then we're only going to use the first chunk for the smaller ones. Because I think it's a little easier than creating separate ones and multi-dimensional arrays. People don't like that. So, all right. So let's say that we will do, we need to use mu to start as the mu, and then we're going to add in these random numbers. Also, let's set our random number generator to some default value. Otherwise, it'll give us something different every time we run it. This just seeds it. Okay. If you want to use a random number generator that's normally distributed, we use rand n. And I believe that you hand this thing just the dimensions that you want. I want there to be n a rows and m columns. Okay? So that each column gives me a different sample. Okay? All right. And then we have to multiply that by the standard deviation, so sigma. Okay. And then let's just print out like a little bit of this because I never trust myself. When I generate stuff, it's reasonable. So let's do that. Let's print out maybe like 1 through 3, and then like 1 through 5 or something like that. So a 3 by 5 array of these values, and we'll also display the length of, or the size of data A, just to make sure we understand what's going on in there. What size inputs must be scalar? Help rand n. Am I right? Oh, of course.
Is it because you didn't select the value on NA?
Yeah, that's correct. So let's use the last value. What? Oh, it's because I didn't use a semicolon or a colon there.
There you go.
Hurrah! So, that looks like it's wildly distributed around 27, right? So, makes sense. And there are 100 rows, which corresponds to, so a column then being a sample, and then there are 200 samples. Sweet. Okay, so that all is making sense. We have ourselves some data to work with. So now when you want to look at the distributions, right? We want to compare the distributions. So we have to, plot using, histogram. So let's try that. So let's open up a figure. And then let's say that, let's just start with doing one of them, and then we'll figure out how to do a loop of them, right? Because I think that it's easier to think that way. So we start a figure, and then we're going to do histogram of, and then you hand it the data that you want to give. Wait, we're not ready for this yet. Why are we not ready for that?
We don't have any teeth.
We don't have our means yet. We don't have our means because we want to look at the distribution of the means, not the distribution of the raw data. Because
So you take the means of those at set down.
right, so
Can we
the
split
mean of each sample.
Wouldn't that be just the mean of this data
Yeah. So mean.
A? Mean of A.
So I'm gonna call it mu a. So what you do is you take mean of data A, and you have to tell the dimension over which to take the mean. So we want to do it column-wise, which I believe means we need to put in 1 here, over the first dimension. So let us see if we're right. There should be 20 values that come out. We are not right.
I was going to say, wait.
No, wait, not 20, 200.
Oh,
So
that should be.
So then let's look at what is the size of mu a. 1 by 200. So that's good. What? Shh.
The kernel has died.
That's okay. We'll get chicken still. Okay. So that was an Aaron joke.
Yeah, it was an Aaron joke.
Okay. I'm learning.
I don't think he approves of your numerous songs.
Okay. So we have our means now. So our means are what we're looking at the statistics for, right? But what's interesting is we really want to have a mean of each sample size of the data, right? So what we want to have is the mean for the first 10 rows, and then we want to mean for the first 20 rows, and then we want to mean for the all of them, right? So we should put a little loop in here, and we should say for I equals 1 to the length of our, we actually have a number for this already. So we want to do it for each of our NA, so I guess length of NA, which is 3, right? But we don't want to hard code in anything we don't have to. We can put in the mu a's into, say, a different row of the new mu a array. Now, it's probably good. It's good practice to pre-allocate, right, by initializing the array. Remember this little idiom that I use: NaN times 1's. The size that I want here is going to be the length of NA rows and M columns. And then for each row, I'll have the means for that sample size, right? So that means that I need to come in here and I need to say, okay, for the ith column, for the ith row, all the columns should be populated with the mean of data A, not of the whole thing, but of let's see, the one through NA of I and all of the columns, right? I think that's going to give us the first 10 or the first 20 or the first 30 rows, or not 30, 100 rows, and then we should end up with something that is 3 by 200. Yeah, I didn't really need to print out all those nans. 3 by 200. What do you know? No! It's okay.
Well, how do you know that it's going to do 20, 10, 100, like 100?
Ah.
Because it's coded into an A?
So because it's in NA, so I'm going from 1 to NA of I, so I'm taking...
NA is 10, NA is 20, NA is... That's clever.
Yeah. I thought so. Thank you. You guys might think that compliments don't mean anything to me now. They do. They do. So, okay. Okay, so we've got ourselves a mu... That was good. Okay, so now we're ready. Right? It's good. You got to keep me humble. I appreciate it. Okay. So we want to do a histogram. Let's do a histogram of just the first row of mu a's first. Okay. So mu a. So the first row, all the columns, and let's just take a look at it. Take a peek. Not what I was expecting. This is how I code. I don't know if you guys think that I know how to do everything, but I don't. It just did the default number of bins, which surprises me that it didn't pick a better number than that. But let's do. I think it just shows one bin. So let's choose like
24 to 25.
30 bins. What?
It's
40.
it's only getting values between.
What does our mu a look like? Oh. Do I have these things in dimension wrong? What if I just look at mu a? Yeah. I want to look at. Oh, I meant to do 1. Right? Isn't that what I put? Yeah. The first row, all the columns. If I look at this, oh, they're all the same value. Or they're like really close.
Because your random number generator is doing the same thing every time inside the sample set.
No, it shouldn't. Oh, is it?
It's giving every single set the same set of random numbers, which means the first row would always be the same number. When you do Yeah,
It's supposed
That's what it
to.
looks like.
It's supposed to do. I mean, these are different, right?
You're saying like the bins are all the same.
Right. So the mean of all of them is all the same because it's all the same.
Yeah, I mean, but we only have 10 samples in the first one, so the means should be different. So if I look at my mu a's should definitely not be identical, right? Like if I was to sum up the first, so if I looked at all of the rows, so there's only, well, I guess 1 through 10. There's no way the means of these are all coming out the same.
I don't want to do it.
I mean, that's what I thought I was doing here,
It's
But I
coming
guess-
out all the same.
but it is. So cleverness, not so much. Something is going on here. Am I taking the mean over the wrong dimension, possibly? No, I thought that was right. The first dimension, let's, as we go through here, let's compute what the size of this thing is that we're giving it. Oh, 10 by 1. So why is that happening? Why am I getting 10 by, I should be getting a 10 by 200, I thought.
Yeah, because your m is a constant. It's not a rate. Right? It's just 200.
It's 200, but it shouldn't.
It's like a 1 by 1 matrix.
Right, but that, I think, oh, I get what you're saying. I should be doing that. Nope. Yeah, because if I didn't change that. There we go.
Yeah.
Nice. Now we're actually being clever. We weren't before. We were just wrong. Okay. Very, very nice. So now this should look cool. And now,
Rainbow spaghetti.
now this should look better. Hooray! This is how I code. Exactly like this. Okay. And then, and now probably I can let it use default, which is usually pretty good. Okay. Whew. That looks, I don't know, normal-esque, but not exactly normal, right? Because this is for our smaller. But let's do like 2 then. Okay, that one looks better. And then 3 should look best. Well, not bad. So let's look at making a loop then. Figure.
Well, one of that looks perfectly normal, right? Because one of you skewed towards whatever you set the mean as, so it's 27.
Yeah, I mean, it's pretty good. It's pretty good. And then I want to do for I equals 1 to length of n a, and then I'm going to say, okay, I think I can do like face color equals, I want to say, C equals jet of 3. And then I can say C of I, H dot face alpha, which gives me the opacity, equals, we'll call it like 0.5. And then, but I gotta go, I did that, made that mistake before. And I gotta definitely do a hold on here. Oh yeah, that one's pretty. It's so pretty.
I know what I've taken away from this.
What's that?
after years of MATLAB experience, you will not be good at actually coding. You'll just be really good at formatting the colors and
Yes,
fonts of your.
and you get better at debugging. Those are
Which
like,
is probably the most two important skills in MATLAB.
I
yeah.
have no idea how to do the actual code, but I know once I get the code, I can change the color and the opacity and.
Yeah, that's what
Yeah,
matters.
MATLAB, we're like,
So, anyways,
that's
those are our histograms.
Right.
So, things that we're picking up here, as you increase n, the mean, our spread of our mean is shrinking, right? Which makes sense, right? And it gets more and more normal, and that's kind of, those are the main things that we notice. Okay, now I want to do the t thing, right? Let's just do the t thing. So I want to know, and we'll use the table instead of doing, we can use MATLAB's built-in stuff, but let's just use the table. In order to do that though, I need to know the standard deviation of the means. We didn't compute that, we just looked at the distribution. So the standard deviation of the means is S mu, right? Equals, and we can just compute it directly for each of these. So I'm going to have 3 of them, and standard deviation is a nice function that allows you to tell it the dimension. You don't have to loop over it. So we can just give it mu array, and we're going to tell it the dimension to go over, and I believe the dimension is going to be the second dimension this way. If we're right, we're going to get 3 values out. W must be help STD. I bet that never gets typed into Google. It's the third. It's the third one. Pass-in flag equals 0 to use the default normalization. Yeah, that's correct. So I just need to use 0. There we go. All right. So there are standard deviations of the means, and we can use these values. So our confidence interval that we're trying to compute are based on the percentage, and then we got to multiply. So what they're going to be is our mu. They're going to be our mean of our mu a's. We'll just put it in a loop because it's easier. We probably don't need to, but.
Did you send this to like Slack or something?
Totally. Yeah, I will do it.
No Slack. No.
That was more like on my level.
I'm tired.
You should probably, yeah. Okay, and so we're going to take the mean of that, and that's going to be our estimate of the mean. So the mean of mu a, we're going to take the ith row and all the columns, and we're going to add to that our t value, which we need to look up 3 t values, right? So our t array is going to be whatever we find those to be. We're going to take our t value, the ith t value, and we're going to multiply that by the standard deviation of the mean associated with this, S mu of I. Okay? And this is just going to print those out. So we could save them, but we're just going to print them out because it's our sort of final answer. So we have look up our t values, and then we're good, right? So we need the we have our n's, so we know our n's, right? Our degrees of freedom, and we have our confidence requirements, which is what was it? 99%? What did I say?
Yeah,
99%. So let's look at this, we see 99% is this column here, right? The fourth column from the end. And then the first set, we had 10 data points, or our sample size was 10, so our new is 9, right? So 3.25 is the first one. And then let's go back, and the second one was for 20, right? 2.861. And then the last one was for 100. Is that right? So it's
You could interpolate, or we could just pick the 100 value.
2.626. Oh man. All right. And then I think we're going to get out probably some error. Let's see. Oh, we want to do plus and we want to do minus too. So we want to stick out an interval. So let's do minus, even trickier. -1, 1 times that. All intervals. Okay, so let's take a look. Our 99% confidence interval for sample size of 10 came out to be 17.9 to 36.3. So pretty big spread for the mean. This is our confidence in the mean. We doubled the number of samples. We tightened up, right? We tightened up. We went from 20.9 to 32.9. Remember what the actual value is? I don't. What was it? 27? Okay. And then we went up to 100, sample size of 100. So in each bin we had 100 samples. We have a better estimate of the mean. Remember, it was tighter grouping. Our 99% confidence interval went down to 24.4 to 29.7. So we're getting pretty good. We're tightening in, right? So if you came back up here, it makes sense. The green data is the data with the 100 data points in each bin, and it's a tighter grouping, right? So our confidence interval, it makes sense that it's shrinking down. So it's from like in here to in here, our 99% confidence interval. Okay. Whew. How do we feel about how is student confidence right now?
40%.
40%.
Solid 35 for James.
Okay.
I'm a bit upset that you fudged that 100 thing, not 99. Still.
Oh, I did.
Yeah, but whatever. It's fine.
We didn't interpolate. We probably should have. You know, and you can also there's a I don't know what the command is. Student.
Help, student.
Uh,
I'm falling.
student PDF. I don't know. MATLAB. I'll Google it. Student PDF.
So complete scientific.
TPDF.
For Jupyter Notebook, so is this like a website you go to, or do you have to install something and then use it?
You gotta install stuff. So the Jupyter Notebook is actually made. They're trying to go more and more language independent. So they started out as Python, but now they're including kernels from other languages, so you can write other languages in the same interface. But it's a web application that you run locally. So you run it in a web browser, but all the files are on your machine, and you have to like boot up the little server. It's a little bit annoying to get started, but once you get it going, it's kind of fun.
So you can like make a MATLAB file, like a .m file, and then save it, and it'll run while you're on the Jupyter Notebook, and then when you translate it onto a regular MATLAB, it'll work just fine.
So you can export it. You can export. So I have what's called a MATLAB kernel running on this. So it can run MATLAB code. So all the code in here executes as MATLAB code. then when what I'm going to do with this and what I do with the lectures now is I can export this notebook as an M file, so that you can then run it in MATLAB directly. You can always copy and paste the code directly over into the MATLAB interface if you wanted to.
But there's no real reason to run this if you were just running it as a MATLAB application instead of running MATLAB. There's no
Right.
advantage. You
There's
don't
no
get to solve
advantages.
stuff.
Yeah, so this is a nice interface for doing the sort of stuff that we're doing, just sort of like, one cell at a time, evaluating stuff. It's kind of nice. It is a little bit of a thrash to get it working with MATLAB right now. There's a MATLAB kernel, and you have to install it, and depends on, you have to have like an updated version of MATLAB for it to work, and it's kind of,
So you have to have the program you're running in order to use the kernel.
yes.
Okay.
So
I tried to work around getting MATLAB.
And I was about to say,
That was good.
why would you-
I'm pretty sure, actually, I say that, I'm almost positive that is true. I'm 99.9% positive that you have to have MATLAB.
Within 3 standard GPUs.
But that
Yeah.
seems like too good of a
That's what the CMD.
Yeah, I think that's right. So
Hey, make sure you can get the right.
but like you can do Python in these. I mean, it was built for Python, so that works the best. But yeah, I mean, I like the notebook interface. I think it's pretty cool, and you can write. So in these other cells, you can write like anything you want, like MATLAB, or it's not MATLAB, LaTeX equations in there, and it renders them nicely. So it's Jupiter, yeah, spelled like.
No.
Did you put that in the first few notes that you started making with this?
Yeah, spelled like that.
It's in one of the.
Makes more sense.
So it's pretty cool interface. I like it a lot, and it's definitely like picking up speed. It was sort of its own little thing for a while. It's called IPython and whatever. But then I think that they're getting critical mass now, and I think that a lot of languages are just going to use this because people like using a notebook interface. Mathematica, I think, was the first to do it, and then some of these other languages have started to want to do it too. So it's pretty cool. I like it a lot. I've been trying to use it more and more. So.